Hi, in this video I'm going to do an acoustic test which is called a frequency response test on the Behringer U-Phoria UM2 audio interface. So this is basically a sound card and its job is to convert analog signals from your instruments, your microphone, whatever you're plugging in here, and it's converting it into digital because you are going to use it on your computer. Now the audio interface I have at the back there is just an M audio M track, and I will be doing a video comparing these two, but in the meantime I just want to show you what my setup is. Now the M audio at the back there is just for my microphone when I'm recording the YouTube video, but what you're seeing here is a function generator. The purpose of a function generator is it allows you to select a variety of frequencies. So if you want to say to have 10 Hertz, well, there we go, and then you can adjust the frequency with this knob here, and as you adjust it you can go from say 0 to 20, and then there's 100 Hertz, and again it's a factor of 2. You can go almost at 0 all the way up to about 200. So there we go, and then you go kilohertz, 10 kilohertz, so that will be, you'll see there 20 kilohertz, and then we're going out of the frequency, the audio spectrum, to 100 kilohertz and megahertz, which I won't be doing. Now if you look on the left hand side here, I have an oscilloscope, and what an oscilloscope is, it's a device that shows you the waveforms or the signals that you are inputting to it. So this is the lead for the oscilloscope, and there you can see it's telling me I have a signal with amplitude 407 millivolts RMS, so it would be the root mean square of that wave. And if you have a look here, you can see how I can adjust the amplitude, and look what happens when I increase the amplitude. It is telling me I'm going into clipping. It's too high for the input. So you can see how when I reduce the amplitude here on the function generator, it's almost like the volume of your instrument. So the purpose of a function generator is it's a testing device because it allows you to inject signals into whatever device you're going to do it with. So here I have the Behringer audio interface, and this over here is the lead of the oscilloscope, so I'm measuring what I'm injecting in here. Okay, so let's sweep through these frequencies. Now if you look on the oscilloscope here, you can see that the other reading there is giving me a frequency. Can you see it saying there, let's say that is, there we go, 58 Hertz. So audio is in the range of 20 Hertz to 20 kilohertz. Although that is arguable, there are publications saying that humans can perceive, and I didn't use the word here, we can perceive frequencies above 20 kilohertz. You're welcome to go look at those studies. I can post them online if you're interested, because people who listen to live music with instruments that go above 20 kilohertz and all the harmonics of drums and so forth prefer the sound when the sound has a higher frequency range. However, for digital recording, we tend to only go up to 20 kilohertz, and then when we do our mix downs, we tend to also go only up to 20 kilohertz, and that's also because of the limitations imposed by our analog to digital and digital to analog converters. Okay, so if none of that makes sense, don't worry. The purpose of this video is to see the frequency response of this device. The goal is as follows. When you create a sound card, you must make the sound card have a flat response. So no matter what frequency I set this function generator to, it should not change the voltage. Can you see it says there 310 millivolts? Doesn't matter if I'm at 15 kilohertz, it should still be, well, there it's gone to 309, but really that's very close. 310 millivolts at 12.78 kilohertz. And as you can see, I'm sweeping through, and the reason why it's called a sweep is if I just put this on manual mode, I'll show you what is happening here. It's called a sweep because if you look how I'm sweeping through the frequencies, that's a low frequency. You can see how wide the waveform is. And as I sweep, you can see how many more sinusoidal waveforms there are in that same period. Period is kind of a time range. All right, so there we go. And you can see I'm sweeping through the frequency right up to 20 kilohertz. There we go. and you can see how that waveform is being concertinaed in there. All right, so obviously you'd have to adjust the time base of the oscilloscope if you want to look at that waveform. All right, so this is the reference. The reference is the signal generator, because the signal generator does not introduce distortion. This is a fairly good quality signal generator. It's called a Topwood, made in Taiwan. I've used these extensively. I've made many active filters and Bezel, Chebyshev, 4th order, 6th order acoustic filters, and this device is very accurate. You can see the waveform. It's very clean. It does not introduce distortion. So the question is if I input an 18.69 kilohertz waveform into this Behringer, will I get an 18.69 kilohertz waveform on the output still within the same amplitude? You see, the audio interface has the ability to amplify, but if I don't change any of the settings and I go right through from, say, 550 hertz all the way through, you can see how this amplitude is not changing. The only thing that's changing is the frequency. And the reason why is because, say you're playing a drum, you don't want to have certain frequencies amplified while other frequencies are attenuated. You want your sound card to represent the exact analog signal that was here. Therefore, it should give you a uniform envelope on the output. So how am I going to measure this? I'm going to sweep through like what I'm doing now. I'm showing you what I'm doing here because shortly I will then show you the output, and I'll be telling you I'm sweeping through, and I'll be telling you the frequencies, but you won't see me doing this. All you'll see is the output on the screen. So what's going to happen is I've inputted it here. Here's the audio interface. It goes through to my computer digitally. There's the USB. It's being digitized at 48 kilohertz. I'm not sure the bit depth, but it's being digitized, and then I will show it to you on my graph here, my software that will show the output. So it's going to, using this graph here, once I get it going, you will be able to see the signal on the computer screen and how accurate it's being represented, meaning how good is this device at changing this analog signal and outputting it into a digital signal, and then my computer will then measure that and check that it is correct across the entire frequency range. So when you buy a device, it normally says frequency response, and there you go. Here are the specifications, and you can see there it says there, frequency response 10 hertz to 50 kilohertz at minus 3 decibels. What that means is if you had to look at the curve, it would look like this, and at the minus 3 dB point, it should be at 50 kilohertz. I've done some basic testings already, and I didn't find that I got to 50 kilohertz. I'll just show you what I found. All right, so without further ado, I'm going to now do the frequency response test on the Behringer U-Phoria UM2. And what I also will do, and I'll just show you now, is I'm also going to just put in a square wave. And this is quite useful because in acoustics, it's quite nice to look at a sound card's square wave response, because we can get to see how it responds to harmonics. You see, to make a square wave, it's an infinite amount of sine waves. So that means it's many harmonics above the signal value. So there you can see an example of the square wave, which I'm going to input into the device. And what we should be getting is a square wave on the output, obviously after it's been digitized, but we don't. We don't get that, unfortunately. So I just want you to see what it should look like. Look at that vertical, flat, vertical, 90 degrees, 50% duty cycle, which means the energy in that area should be equal to the energy in that area. It means that the leading edge here and the positive going wave should be equal but opposite to the trailing edge here and the negative going wave. You can see that the period from there to there and from there to there should be matched. So that's what it means when you say 50% duty cycle. Okay, so let me test this device. Here we go. Okay, so here I'm going to do the test. I'm just going to use a software called Cool Edit Pro. It's from back in my day when I used to do sound recording, and I'm just using it as an oscilloscope. So you saw the oscilloscope on my desk, but now I'm going to use this acoustic software as a type of oscilloscope. And I've used it many times and done quite a few acoustics tests with it, and it works very well. So what I'm going to do is I'm going to say the sample rate, I'm going to put it to 192 kilohertz. The higher the sampling rate, the better it quantizes the signal. And then I'm just going to put it on mono because I'm only going to test one channel. And then you can set the bit depth. You can do 32-bit. I've already done the test. It doesn't make a difference in this test whether I choose 16 or 32-bit. Right. So there we go. The capture is ready. I'm now just going to calibrate it. And by doing that, I'm going to just put a 1 kilohertz signal. My function gen is set to 1 kilohertz. And what I want to do is I just want to make sure that it's on the correct voltage. Well, on this scale on the right hand side here, you could call it decibels. It's a nominal scale. I've got it set to nominal, so you can kind of think of it as the volume or the amplitude of the wave. You can see as I increase the amplitude, how it affects this waveform. So this here on the horizontal axis is time. This here is amplitude. Very similar to the oscilloscope. Right, I'm just going to calibrate it onto this line on the dot. Right, so I have now calibrated it. I've calibrated it to 0.8. If you look at the scale here, you'll see that is 0.8. And this is the line of 0.8. You can see that if you look at the sine wave, it reaches 0.8. So I've used 1 kilohertz as the calibration amount. And I'm just going to shift this waveform here. And now I'm going to just delete all of this signal that I've just taken. I'm just going to delete it. Right, now I'm going to vary the frequency. I'm first going to test the very low end. So that is going to be the 0 hertz to about 20 or 30 hertz. And then I will sweep from about 30 or 40 hertz all the way up to 20 kilohertz. And the reason I got to do that is because my function generator has that feature. I can't sweep from 0 to 20 kilohertz. I can, because the range is too wide. So I have to pause and then change the range. All right, let's start. So there we go. We've got a very low frequency. This is 1 hertz. And as you can see, the amplitude is very low. So this is kind of the beginning of the signal input that the Behringer can handle. And there you can see as I increase the frequency, look at that signal growing. Look at that. Now I'm at 3 hertz. I'm now at 4 hertz, 5. There we go, 7, 8, 14, and there you can see I've reached a kind of a steady state. We call it a steady state when the amplitude no longer changes. I'm now at 25 hertz. You can see it's a little bit uneven on that roll up, but let's try that again. Let's look at 25 hertz. So from about 20 hertz, it should be highly stable. Let's just go 10 hertz again. There we go. That's 10. And as we increase, we go to 25 hertz. It's not too bad. Right. I'm just going to pause the waveform here. And now what I'm going to do is I'm going to get ready for a full sweep going from about 40 hertz or whatever I can get it down to. Yeah, there we go. I'm just above 50 hertz. And here we go. I'm going to sweep all the way to 20 kilohertz. Right, I'm now at 50 hertz. I'm now at 150, 300, 500. I'm at 1 kilohertz. And moving through, I'm now at 5 kilohertz. And look how stable that amplitude is. 6 kilohertz, 11, 12. And this is where it's going to get interesting, or it might get interesting. It's usually over about 16 kilohertz. Sound cards generally go into a bit of a wobbly, meaning the amplitude starts to get a little bit unpredictable. So let's go. Let's see how stable this Behringer is. I'm now at 17 kilohertz. Still stable. Well done. I'm now at 18 kilohertz. Still stable. There was almost no change to that amplitude. I'm now at 19 kilohertz. And I see some, yeah, there you can see some instability coming in. Can you see the amplitude is kind of drifting up, down, so there is a little bit of a stability issue there, but in terms of decibels, it's very little. In terms of whether it's within its accuracy, well, I'd have to take a measurement if it's still within the percentage that they highlighted. Right, let's go to 19.5. I'm now at 19.5 kilohertz. For the most part, it's still very good. Right, I'm now at 20 kilohertz on the nose. That is 20 kilohertz. Some attenuation took place. I don't know if you noticed that. From 19.5, then 20 kilohertz, we had a little dip there. Now I'm at 20.5. That's 20.5 kilohertz, 20.5, not 25. So you can see how it is now rolling off. And let's go above that. I'm now going to pause it. Alright, I've now adjusted my function generator so I can go above 20 kilohertz. So I apologize for that little blooper there. Alright, so let's go back to 18 kilohertz, and let's now see what happens when we sweep from about 18 kilohertz all the way to 25 kilohertz. I'm at 17.5. I'm at 18.8. I'm now moving through. I'm at 19.9. I'm at 20.5. So I'm sorry, it does vary quite quickly, but now I'm at 21.5. And you can see that attenuation is quite excessive. But remember, the acoustic range that is generally accepted is 20 hertz to 20 kilohertz. In terms of this device, this is 20 kilohertz. It's still at that amount of 0.8. It is, I'm not complaining about it, because if you look at the 0.8 point, if you look at the 0.8, there it is. And you can see this waveform is maintaining that 0.8 while at just under 20 kilohertz. All right, so if I go above 20 kilohertz, boom, there comes the attenuation. The card is not made to handle frequencies above 21 kilohertz. And let's go a bit more. I'm now at 27 kilohertz cutoff. You can see that the roll-off became pretty steep, and there are very little frequencies coming in. Now let me just roll back just to about 23. Let's see if I can roll back to about 23.5. That's 18 again. Alright, that is 23.5 kilohertz. You can see that that is a considerable drop from the original calibrated level. Okay, so that's the frequency response of the device. If we just review that for a second, just to talk about it. Look, that was the roll up. You can see there was a little bit of instability. Not terrible, because remember that the device says that it can only do, what did it say? It said the specification was from 10 hertz. And 10 hertz was about here. So you've got to still keep in mind the minus 3 dB point. And the minus 3 dB point would be somewhere at about 70.7%. So if you look at 70% of the graph, well, that seems about right. So I wouldn't be too upset about that. Then you can see it's fairly stable here. It does take a while to reach its calibrated level, so this is a little bit of attenuation still happening on those low frequencies. And then as we move through, if you look at, we do the sweep, you can see that it's fairly stable. There was a little bit there as well, but for the most part, not too bad. I would say that's pretty good. This is quite minor, because if you're looking at it on terms of the levels, that's 0.8, and then it got to about 0.75. So that is a very small amount of deviation. Although it has to be noted, it did deviate. Right, moving through, there we go. Not too bad. mostly hanging around the 0.8 level. And then when we got to the upper frequencies, we saw, I did mention these particular frequencies. You can see how there is some oscillation happening here. So this is not a greatest response in this upper frequency band, and there's slight attenuation beginning to happen. And if you want to just see what is going on there, you can see that these are the sine waves. You can see these are the sampling quantization levels. Remember, to sample at 192 kilohertz. If you want to just have a look at what it would look like when the waveform is a much lower frequency, there's a low frequency wave, and if you can have a look at how many quantization points there are, there's much more. Remember, it's all got to do with the frequency. So there we go, and here we come up to this point, which was about there, right? So we're about, where did it start to get a little bit wobbly? Yeah, there's getting a little bit wobbly. Okay, so then we got to the 20 kilohertz range, and above that we saw that it does attenuate quite aggressively. But overall, I wouldn't call this studio quality. I'm not saying that you can't use this in a studio. I wouldn't. But I wouldn't use other devices as well. This is only marginally poorer than the M-Audio M-Track 2x2. So I will do a comparison of these two, but keep in mind that this is a very cheap device in terms of studio equipment. So overall, I would say it did a pretty good job for the price. Okay, then I just would like to do one last test, and that is just let's shove a square wave in there. So I'm putting in a square wave. I'm going to put it at 1 kilohertz. I've showed you what the square wave would look like and what it should look like. I showed you on the oscilloscope, and let's just look at what it looks like on Cool Edit Pro. So there we go. Oh, whoops. Let's carry on with the recording, and there it comes. There's the square wave at 1.02 kilohertz, and if I just pause this and show you what it looks like, that is the square wave on the UM2. If you look, it's fairly vertical, got a bit of overshoot there, then some ringing, and then it ends with an overshoot and fairly vertical on the trailing edge. Not a bad response for a square wave at 1 kilohertz. Again, ideally it would be flat at the bottom, completely 90-degree vertical line here, followed by a flat response, followed by a vertical line here. But if you look at this ringing, it's not too bad. If you're wondering why it does this, it's because the card cannot handle all the harmonics available. You remember that the frequency range of the card is limited to about 22 kilohertz at the 3 dB points. So if it was limited at say 80 kilohertz, well then this square wave would start to look more accurately represented as a square wave. Although if you look at the formation of this, it's not bad at all. I would say this is quite fair. Obviously it is an entry-level card, but you can compare the 1 kilohertz square wave on other devices, and I did do these tests for Creative, and they had a sound card called the Audigy, and if you look at the square wave response, and that was probably about 15 years ago, is pretty remarkable. So we got to just think about the square wave response in telling us how the card handles the harmonics. Okay, so overall, I quite like the frequency response for an entry-level device. I'm going to say that it mostly does what it's supposed to. I'm not going to complain too much about some instability at parts, some drifting. Other than that, I just didn't really like this. But other than that, this oscillation here, it's not very high. It's different if you would see these going like this. Then that would be quite bad. So I don't know if this is ringing or what. But the next thing would be acoustic tests, actual tests, human ears. All right, thanks for watching and cheers.